Hi everybody, here's a short video that explains how to do the problems on the first midterm exam, which covered chapters 1 through 4. In this problem, we're given a graph of velocity versus time for a particle that's moving along the x-axis. So it's just going back and forth like this. Now a lot of people tried to solve this problem by trying to calculate area under the curve, and while it is true that the distance that the particle has gone is equal to the area under the curve, that doesn't mean that you should just do the 1/2 BH and kind of count up the squares underneath here. Nobody that did it that way really met with much success. What you need to do is to recognize that you can use the kinematic equations for constant acceleration. The reason you can use them is that, for instance, in this time interval, the slope of velocity versus time is constant. This is a line. And because we know that the acceleration is the slope, or the derivative of the plot of velocity versus time, we can use this. This is the equivalent equation on the equation sheet that says this, v naught x plus axt. This is basically y equals mx plus b. That's what that equation really says. Okay, so what we're going to do is we can find the acceleration in each of these three time intervals. Here the acceleration comes out positive, here it's negative, here it's 0. So we could do that, or we can just go straight to finding the position without finding the acceleration, and we can use this kinematic equation. Either way is fine. So this kinematic equation relates the position at any particular time after t seconds have elapsed, taking into consideration where you started and what the speed was at the beginning and end of your time interval. So when you apply this to the first time interval, it starts at x naught, which is equal to 0. It ends at position x, which is what you want to solve for. It went from here to here, from 0 to 3 seconds. That's why you plug in 3 here. And it started at 1 meter per second, it ended at 5 meters per second, so you'd have 1 and 5 here. So you could solve part A like that. Now for the second question on here, t is equal to 7 seconds, what you would do is use the same exact equation, x minus x naught equals v naught x plus vx over 2 times t, except here, if you're trying to solve for this, what you do is this is whatever your answer was here. Okay, so your initial position for your second time interval is equal to your final position from your previous time interval. So the v naught x and vx would be here and here. v naught x, vx. And then divide that by 2. The time here is not equal to 7 seconds, it's how many seconds elapsed that it had that particular acceleration. So this is 4 seconds goes here for the second time interval. And you do the same thing for the third time interval. To figure out when the particle is at rest, a lot of people seem to know that the particle was at rest here. That's when velocity is equal to 0. But here you do need to find the acceleration. Okay, so it's your delta y over delta x, or your delta v over delta t. So you're going to find some negative number for this. And then in order to find the actual time that this occurs at, is that you have to plug it back into this equation. Okay, so the acceleration that you get here, this negative number, okay, this negative number gets plugged in here. The initial velocity is 5 meters per second. The final velocity is the one that you're interested in here. This is the velocity when it's at rest, which is 0. So it starts off at 5. You have some negative number for your acceleration, whatever that came out to be, and then the time that has elapsed is what you're trying to solve for. Okay, so here the time comes out to be 2 point something seconds. Now that doesn't mean that suddenly we're over here. What this means is that it's 2 point something seconds after the start of the time interval, which is 3 seconds. So you have to add 3 seconds to that, and it came out to be 5 point something, I think 5.2 seconds. All right, and the next problem, this is the projectile motion problem. We did not need to find the velocity of the camera when it hit the ground. I highly recommend drawing a very detailed diagram here. Draw a big diagram so you can actually see and label everything into the problem. So what's happening is that the parachutist starts off up here. Okay, so here he is up here, and his initial velocity looks like this. Now his velocity is constant, so he just kind of keeps coasting all the way to the ground. Okay, he lands way over here somewhere, and this is the ground. All right, so, and it's flat. So he lands here at some time later. On the other hand, the camera, he drops the camera, and it has some initial x component of velocity, whatever his was, but then it's free to travel at whatever speed gravity tells it to travel in the x direction. So while it keeps, he and the camera keep the same v naught x throughout the entirety of their flight, they have different y velocities. Okay, v naught x is going to be equal to 3 cosine of 25. V naught y is equal to minus 3 sine 25. Now it doesn't matter if you put the minus sign in by hand like I did, or if you put sine of, positive 3 times the sine of negative 25, this term should come out negative. Okay, don't put it in twice. Don't put the negative sign in twice. Okay, so here we would like to find what that height is. We know that it takes 6 seconds for the camera to hit the ground. And so what we're going to do is to use this equation, y equals y naught plus v naught yt plus 1/2 ayt squared. This is for the camera, okay? So the guy and the camera start at the same height. The thing lands on the ground, so that's at a height 0. We'd like to find out what that initial height is. We know that it's going to have this term is going to be negative. Okay, so this is negative whatever that came out to be. And then of course your AY is 9.8 meters per second squared, and it takes 5 seconds to hit the ground. Okay, so your Y naught comes out to be something close to 200 meters high. Then what we want to do in the second part is to find out how high is the guy when his camera hits the ground. All right, so how do we do that? He's actually going to be directly above his camera because he's been moving at the same speed as his camera in this direction. So he and his camera are both going 3 cosine 25 meters per second, except after 6 seconds, he's here because he hasn't fallen very far. And the camera is on the ground because it's been speeding up and therefore tracing out this parabola. So for his height above the ground, you would use the same exact equation, y equals y naught plus v naught yt plus 1/2 ayt squared, except his acceleration in the y direction is 0. He started at the same height as the camera, so he starts at this y naught, except we want to find out where he is after 6 seconds. So this is going to be minus, so your y naught from part A, minus 3 sine 25 times 6 seconds, or 5 seconds in this problem. Okay, so this should give you some height that's less than, slightly less than this. He has not gone far, it's just a little bit, but it should definitely come out to be positive. Now for the last part, it asks you to find the distance between these two guys. What you have to do is find the total time it took for him to drop this number of meters going at this speed, find the time that it took for him to land. It's not 6 seconds, but once you find that time, you can find this distance from x naught equals 0 from where he dropped the camera, and you can also find how far the camera went in 6 seconds. So they're going the same speed. It took him, I forgot what it comes out to be, something like 100 something seconds to get all the way here. The camera only took 6 seconds to get here, and then you take the difference between this position and this position. So this A rad is given by this. Okay, so 2g means 2 times 9.8. That comes to be about 20. And then this is given, that's your 1.5 meters. So what you do is solve for v. It gives you something in meters per second. And you take that meters per second, 2 pi r meters is equal to 1 revolution. And then you can solve for revolutions per second. It comes out to be about 0.5 revolutions per second. Centripetal means towards the center, just like this. In this version of the problem, it gave you enough information to find the acceleration of b. So block B starts at a position y0 is equal to 3.5 meters. It lands on the floor at a position of 0, and it takes a time of 5 seconds to get there. A lot of people saw the 3.5 meters and 5 seconds, and they said, by golly, I'm going to divide those meters by seconds and get something, but that's not what you want to do. That just gives you the average velocity when it's here, and that is not a useful quantity in this problem. Use this equation, y equals y0 plus v0 yt plus 1/2 ayt squared, where you start at 3.5 meters, that's your y0, you land on the floor, that's 0. This is 0 because it starts from rest. Ay is what you want to solve for. This is AB, and this should come out to be a negative number, okay, some negative number of meters per second squared. Okay, so once you have AB, here's what we're going to do with it. Okay, so at this point we have the acceleration of B is equal to some negative number. So what we're going to do with this, we're going to draw 2 free body diagrams, one each for box A and another one for box B. MAG is the weight that points down, tension points up. And for B, same thing. You got the tension points up and the weight points down, MBG. Now what are these free body diagrams for? They allow you to write an equation that relates all of these different things, the acceleration, the tension, all of the forces in your free body diagram. What they mean is that the forces acting on A are equal to the mass of A times the acceleration of A, and the forces acting on B are going to equal the mass of B times the acceleration of B. Okay, this turns out to be an equation that looks like this. T minus MAG is equal to MA times the acceleration of A. The acceleration of A is the positive of whatever this was. Okay, so if this was negative 4 meters per second, this is positive 4. This term has to be positive because this acceleration points up, this acceleration points down. Same thing for this, except we've got T minus the mass of B times G is equal to minus the mass of B times A. So whatever this negative number was here, what you've done is to put that number in here. You want this term to be negative. You don't want to take a negative 4 meters per second and put it in negative 4 meters per second here and have this term come out to be negative. Whichever way you do it, it doesn't matter. This whole term has to be negative because it's a vector that points downward. This term has to be positive because it's a vector that points upward. Now you've got 2 equations, 2 unknowns. You can solve for anything that you do not have. Because it's moving at a constant speed, these vectors add up to 0. Okay, that means that individually the sum of the forces in the x direction add up to 0 and the sum of the forces in the y direction add up to 0. Now on this problem, you have to break this into components. Okay, so this component here is t cosine of theta. This component here is t sine theta. Okay, so your x equation looks like this, minus friction plus t cosine theta equals 0. And then this one becomes the normal force points up, the tension sine theta points up, mg points down, that equals 0. Normal force does not always equal mg. Sometimes it does, but that's the physics that you have to know. The normal force is going to equal mg minus t sine theta.